everyone, I'm Jianting Zhang from Sun Yat-sen University. Today, I want to introduce our paper, SkyChain, a deep reinforcement learning-empowered dynamic blockchain sharding system. My presentation will include 4 parts. The first part is the background. Blockchain has been attracted more attention in recent years. However, it is challenging to be widely used due to the bottleneck of its scalability. As the following picture shows, the transactions per second, also called TPS, of Bitcoin is only 7, which is far lower than 24,000 TPS of Visa. So, why it is not scalable in traditional blockchains? It is because every node of the system needs to communicate with all other nodes of the network, validate all transactions, and store the whole ledger, which are respectively limited by its network I/O, CPU performance, and disk size. To scale blockchain, sharding in blockchain has been proposed. The main idea of sharding is to divide the network into multiple disjoint groups, called shards, to process transactions in parallel. As the following picture shows, one blockchain has been divided into 2 shards, and thus the throughput will become double, and the storage will reduce in half. However, sharding also introduced some new challenges. So it is coming the second part, our motivation. Previous blockchain systems operate in fixed interval, called epoch. Each epoch includes 2 periods, consensus period and reconfiguration period. Consensus period consists of multiple consensus rounds. In each consensus round, a new block will be created and validated. In reconfiguration period, some nodes of different shards will be swapped to resist attacks. Besides, the number of shards and the size of block is fixed in previous blockchain sharding system. However, the setting of these parameters are not adapted for the dynamic environment in blockchain. For example, when there are new nodes joining in the system, the number of nodes in one shard will increase, leading to the increase of communication overhead and decreased throughput. Similarly, when the old nodes leave the system, the shard size decreases, and thus a shard will become easier to be attacked by the malicious node. Otherwise, the continuous corrupting also threatens the security of the system. Therefore, it should take some measures to prevent the potential problems introduced by the dynamics of blockchain. Now, I want to introduce our work, SkyChain. The main idea of our work is to adjust the sharding policy based on the dynamic environment. The goal of our work is to achieve a long-term balance between performance and security. There are 2 challenges in our paper. We should consider how to make a suitable sharding policy and how to efficiently merge or split the ledgers when the shard number changes. The sharding policy can be concluded into 3 factors: the resharding interval, the number of shards, and the size of each block. For the resharding interval, less frequent resharding can save more time for the consensus progress, but it increases the risk of the sharding system. On the contrary, more frequent resharding can decrease the risk of the sharding system, but it intervenes the consensus progress because validators stop processing consensus and suffer from exchange costs of the communication and computation of resharding operation. For the number of shards, there is a formula to calculate the unsafe probability of the blockchain sharding system. As the picture shows, with the increasing of shard size, the system becomes safer. Less shards can maintain the size of shards and increase the resiliency to malicious attacks. More shards can increase the parallelism for processing transactions and reducing communication overhead. However, the probability of forming an unsafe shard will be high if the shard size is small. Besides, a bigger block can pack more transactions, thereby increasing the throughput. However, as the picture shows, it also incurs a significant communication overhead and increases the latency of each consensus round when the shard size is big. Therefore, it is significant to make a suitable sharding policy in order to balance the performance and security of the blockchain sharding system. We propose a deep reinforcement learning-based dynamic sharding models due to the complexity and the unawareness of future blockchain environment. The following picture illustrates our model. The left of this picture shows the transactions among 3 epochs of the system. Different colors represent different shards. At the beginning of epoch T, the leaders of all shards reach a consensus to make a sharding policy based on the current environment of the blockchain sharding system for the next epoch T+1. The training model of the right of this picture is responsible to update the DRL models to adapt it for the change of environment. The next is to address the second challenges of this paper. We propose an adaptive ledgers protocol for merging or splitting the ledgers. This picture shows the process of ledger merging. There are 2 blockchains in this picture. The upper blockchain, marked by green color, is maintained by shard I, and the under blockchain, marked by blue color, is maintained by shard J. At the beginning of the reconfiguration period at epoch T, shard I creates a state block to correct state of the ledger, and shard J executes this process in the same way. After the consensus of new sharding policy made by the DRL-8 model, the ledger of shard I and shard J exchange the header of their state blocks and create a new state block, and thus the 2 shards are merged into 1 shard, which is marked as yellow color in this paper. The process of ledger splitting is similar to ledger merging. After the selection of a new sharding policy, new ledgers create new state blocks to split all nodes of shard K into 2 disjoint sets. Then, nodes of shard K respectively store one of the state blocks according to the shard's information, and execute a consensus protocol to add into the end of the blockchain. In this way, a chain K is divided into chain I and chain Z. Each of them maintains a disjoint ledger in back of the state block. Finally, they will respectively process different transactions in next epoch. The last part is the evaluation. We design three compare sharding algorithms: the sharding policy with fixed sharding interval, the sharding policy with fixed number of shards, and the sharding policy with fixed block size. This picture shows the throughput with different average transaction size. The throughput of our proposed deep RL-based sharding model is higher than other compared sharding algorithms and can reach 10,000 with the 500 bytes transaction size. Another picture illustrates the throughput with the transmission rate, which shows that our proposed DRL-based sharding models performs better than all other schemes regardless of the change of transmission rate. And the TPS can reach 19,000 when the transmission rate is 10 MB per second, with the transaction size with the 64 transaction size. That's all. Thank you.